just wanted to show you guys the basic design of your standard backlight ring light and how they're built. There's 4 buttons underneath. That's the top one, switches it on, and as you can see there's a lot of flickering. There's the second button for mode that basically switches on the cool or warm LEDs, and 2 buttons for intensity. Let's have a look. So let's take this ring apart. Here we can see a nice diffuser ring. By the looks of it, it's approximately 1.2 millimeters thick, frosted plastic, and roughly a centimeter away from the LEDs. It gives you a nice diffusion. So these LEDs have no lenses, and that's done on purpose, because if they would have lenses you would get like hot spots on this plastic, and you want to have a nice even diffusion. By the looks of it, it's mounted directly on the metal, so that's good cooling. And you can see clearly there's an inner ring and an outer ring, and by the looks of it, the warm LEDs on the inside and the cold LEDs are on the outside. Let's have a look at this little PCB. There's one simple microcontroller by the looks of it, and the power goes in from USB, and it's only filtered by a little decoupling capacitor right here. And by the looks of it, that's all she wrote. Just a single 8-pin microcontroller, and we can see here the output to the ring. And by the looks of it, it has 1 positive line and 2 control lines that go to the warm and cold LEDs. And we can see this because we see 2 transistors here. So there's probably just 2 rings being switched via pulse width modulation to get the fading and full on if they are going to be on max brightness, and that's it. So classic 2 transistor setup. What else do we have? A little transistor here. By the looks of it, it's going into the power line of the chip, and there's not much else. There's 4 switches on the back side, and I think there's an LED on there as well. And I'll do a quick reverse engineering. Now, as I thought, it's a very simple setup. So we have 1 chip, decoupling capacitor C1, and the USB goes straight into the chip via this 470 ohms resistor, and that's basically the whole power. It's not filtered or anything. We've got an LED straight out of the pin to ground. That's probably the power on indicator, which we can see here on the back. We just switch the power on, and oh, wrong button, power button. Oh yeah, you can see it goes off when the light is on, and it's on when the light is off. Odd. You can see it's directly connected to the ground without any current limiting resistor, so it relies on the internals to take care of that, so pretty poorly designed. Probably just saving a penny on the resistor. We can see 3 pins. We have 4 switches. Now if there were 3 switches, they could just connect 1 switch to 1 pin, have it internally pulled up, and Bob's your uncle. But in this case, they wanted 4 switches, 3 pins, so I assume they're doing some Charlie plexing in here. Power, mode, brightness controls. Won't go too much into detail, but it's your basic Charlie plexing setup. And that leaves 2 pins for the LEDs. Now the way they control it, very simple. They use an N-channel MOSFET that's pulled down, and as soon as it gets a high, +5 in this case, it will be switching on, pulling this LED arrangement to ground, and it lights up the chain. Now let's have a look at the actual design of the ring. Again, it's an interesting design, but very poorly if you ask me. So I've only drawn 1 section. As you can see here, there's 7 LEDs in parallel, in series with 2 7.5 volt resistors, 7R5, and they put them in parallel to allow for a higher current. So the actual resistance is 3.75 ish. This is not uncommon, just putting some resistors in parallel to get more power throughput. That in itself is good. However, putting LEDs in parallel, and I can never stress this enough, is really, really a bad idea. You kinda will get a failure over time. Now the way this is connected, by the way, this is replicated 10 times, and they're just connected in parallel to the power bus and ground. And this whole setup is duplicated twice for the cool LEDs and the warm. I only drew one, but yeah, you get the picture. Now, why is this such a bad idea? And why do I see this often? I don't know why people do it, but it is a bad idea. Why don't you want to do this? Well, the first place is let's do not share current evenly. The reason is, even if they are almost matched in the factory, they will have a slightly different forward voltage, like 1.95, 2.05. So the LED with the lowest forward voltage will draw the most current. And when it's doing it, it will get hotter. When it gets hotter, the forward voltage will drop further, then it will draw more current, and this cycle repeats, and you will get a thermal runaway, and it will fail. Now when the LED fails, it can fail in two modes, either open or closed. If it feels closed, that's obviously a short, and that wouldn't be good for your power supply. That's the end of it. If it feels open, then the only thing that's happening is that remaining current will now spread out over the remaining LEDs, and the same thing will happen again. The other problem is you will never ever get the same brightnesses, because you can't share the current evenly. It's just not possible. So some will be slightly dimmer, some will be slightly brighter, and some may not get the correct forward voltage and start to flicker. So this is a very bad design, and this is why I don't like these cheap Chinese imports that you can buy for $10 or $20 in the supermarket. Let's have a deeper look, shall we? Now, before I do anything, let me solder or desolder these pins. I just want to do a quick measurement. Get my trusty Hecko. Just quickly and safely desolder these pads. What you want to do is add a little bit of fresh solder. To get them loose. Now I'm trying to look at a phone camera while desoldering these. Let's take this out. So here we can see the actual build a bit better. So we got 4 switches, tiny SMD LED in there, and the microcontroller and the 2N channel MOSFETs. Now let's have a look at these LEDs. Alright, now by the looks of it we have a common plus. Okay. Let's zoom out again so we can see the power supply. Put this away, don't need that. So let's connect the positive, and we have 2 strands, cool and warm, don't know which is which. Connect this one, and let's set the power supply to let's go 4 volts for now, just for safety, and limit it to 1.5 amps. Alright, now we can immediately see it's drawing almost 1.1 amps. So let's switch this off. Let's limit this even further. Go to 3 volts and limit it to 1.5 amps, and now we get a safe situation. See, now it's drawing, well, it's drawing 300 milliamps. If we can get the connection stable, let's try the other ring. Oh, here we go, the warm LED. It's a bit nicer to look at. As you can see, the flickering is gone. I kind of forced the power to 3 volts, so it's slightly underpowered, but now it will actually not go haywire, and you can see the change is now consuming all 70 LEDs, about 350 milliamps, so times 2, that's 600-700-ish milliamps for both rings active, and that's not bad. bit less now due to the resistance of the wire, and we have some losses in the cables, but as you can see it's kind of stable now, so I could probably repurpose this ring. Unfortunately the diffuser is broken and there's some dents in here, but yeah, I don't see any failed LED. Unfortunately I'm not going to, at least not with this board, because like I said, I just don't like this design and I don't like the fact that they are in parallel. So I could probably get them back to work if I redesign this board and make it a bit safer, but I'm probably not going to. I just wanted to show you guys the basic design of your standard backlight ring light and how they're built. Now I don't know which microcontroller has been used here because I'm trying to read it, but it's, yeah, it's wiped off. Can't tell if it's a PIC or an AVR, but it's probably one of these 3-cents microcontrollers that you can probably program only once to keep it as cheap as possible. And I don't feel the urge to reverse engineer it. Like I said, it's a very, very straightforward schematic. If I would have built this, I'd probably used an ATtiny 1632 or just a small 8-pin microcontroller and do it slightly different. I would even omit the LED. I would just use 4 pins for 4 buttons, keep it simple. All pins pull up, active low, and yeah, there's no need for this LED. I mean, it's barely visible as is, and yeah, I don't know. Maybe connect it straight to the power so you can see that the device is powered instead of using a pin to do it. I really don't know why they felt the need to do that. Just a waste of a GPIO. They could have just put the LED with a resistor straight onto the VCC and that will be your power indicator right there. But anyways, I didn't design this. Well, I hope you find this interesting and I'll see you in the next video.